software side of a real-time system, and in particular on Linux when it comes to the software side. But it's very important as a background consideration. It's very important that you really consider the entire real-time system and entire stack, and every component of the stack, including the underlying silicon, the operating system, the networking stack that you support, the user space applications. They all need to be tuned and configured so as to be able to support your real-time workloads. So it is not sufficient to only focus on either the software or either the hardware. You really need to have a broader, comprehensive view of your entire system. Why is that the case? Because each layer of a real-time stack must prioritize the real-time workloads. It must be able to allocate the different resources, whether in hardware or in software, in order to deliver the low latencies and the time synchronization that are needed to support deterministic processes within your environment. So neither hardware on its own or software on their own, neither of those can guarantee a maximum latency on your system because performance is strictly dependent on the overall stack. With this in mind, then, what is a real-time system in the first place? And at its simplest, the purpose of a real-time system is to meet certain timing constraints. We are looking at embedded systems that must operate within a fixed time boundary. And often the success of your operation depends not just on the logical correctness of the operation, whether it is performed in the right way, but also on the time at which it is produced. So if you are unable to meet your timing constraints, often you're going to have failure within your system. Now, I mentioned a real-time stack, which comprises the hardware, the software, networking, etc. Let's now focus on the software side. And on the software side, the software side, Linux is emerging as a valuable alternative to a real-time operating system in order to process deterministic workloads. So the concept of preemption lies at the core of real-time Linux. And preemption involves being able to interrupt the current thread that is executing within the kernel in order to be able to process events that have a higher priority. So essentially, you would be not able to attain a deterministic response time in Linux without having kernel preemption. Now, in the Linux kernel, there are different preemption models, so-called models, and they are essentially modifications to the kernel, and depending on which one you go with, whether you go with the preempt model or the preempt voluntary model, you're going to have a different latency result, a different throughput result, and it's really dependent on what your use case requires. Different preemption model will give you different results on the path toward achieving lower latencies. These are all available within the Linux kernel, but can we do better than that? How about those with very, very low latency requirements that really need to support real-time workloads? This is where the concept of real-time Linux comes into play. And essentially, real-time Linux is Linux with an external set of patches aimed at bringing more preemption into the Linux kernel. And this external set of patches is called preempter-T. Those are patches hosted at the Linux Foundation that modify the Linux kernel in order to extend its versatility, in order to give it the capability to meet real-time requirements in such a way so as to make Linux viable for many low latency, low jitter workloads. The preempter-T set of patches strives for full preemption in the Linux kernel, which means that everywhere in the kernel code, you must be able to interrupt the process that is currently running in order to assign the CPU to higher priority processes. This even in critical sections within the kernel code. Now, preemptivity doesn't necessarily guarantee the lowest latency possible, but if you have an unbounded latency, that would represent a bug, because real time is really about having an upper boundary of time, having a well-defined fixed time constraint. So what is the goal with the preemptivity? The idea is to make all the code preempted and under control of the scheduler. So preemptivity brings a set of modifications to the kernel. For instance, they replace the locking primitives of Linux with spin locks that are aware of the priority inheritance, for instance. But they also bring a lot of other technicalities in order to give Linux the real-time capabilities. So it essentially it makes the kernel more deterministic. It replaces musexes, it changes the scheduler, and a lot of other real-time supporting mechanisms. Now, if you're interested into at a technical level, how does Linux achieve real-time behaviors, I recommend you look into the documentation of the preemptor set of patches of real-time Linux. It's extensive, and you should be able to find all the answers that you want to have about it. Now, I'm sure some in the audience are asking themselves, all right, with preemptor Linux has the real-time capabilities that I require for my use case. But I've also heard about an RTOS. I've heard about a real-time operating system, and that's different from Linux. So how do the two compare together? Now, RTOS stands for Real-Time Operating System, which is somewhat confusing because then what is real-time Linux? And it's just an acronym for a different class of OS solutions that is different from Linux. Linux with the preemptor assumes real-time behavior, and now let's look at what an RTOS is and how it compares with Linux. Now, an RTOS, a real-time operating system, is a valid alternative to real-time capable Linux solutions that use preemptor T. While Linux, as the operating system, is not a hard real-time operating system, just like Linux is not an RTOS is not a general purpose operating system like Linux is. So they belong to different categories. And what are some of the main differences between the two? An RTOS has very few capabilities. It often only focuses on deterministic response times, on very precise control over task scheduling, and they are frequently purpose-built for real-time applications. They prioritize determinism and also bring in predictability into their software. Because of this reason, an RTOS is often very, very specialized. It is resource intensive. It is purpose built. It has limited functionality compared to a general purpose operating system like Linux, because an RTOS is truly focused at one specific function, which is achieving deterministic response times. This is in a nutshell what an RTOS is. On the other hand, you have a general purpose operating system like Linux, and with preemptor T, you can improve the real-time capabilities of the Linux operating system. Preemptor T is a collection of patches that together reduce the latency that the Linux OS will give you, and Linux with preemptor T can improve its own responsiveness to real-time workloads. Together, Linux plus preemptor T are suitable for many real-time applications. But it's important to understand that, again, we're talking about two separate classes of operating systems here. You have an RTOS, specialized, purpose-built, resource-intensive, very few capabilities, very limited functionality, but really good at scheduling tasks, very precise single-purpose function devices. On the other hand, Linux with preemptor T adapts, it changes, it extends the functionality of a general purpose operating system to meet real-time capabilities by bringing preemption into the kernel. And even though Linux is not an RTOS, with preemptor T, the performance is often sufficient for many real-life low latency workloads and applications. So you really need to consider the requirements of your use case, of your applications when making a choice between the two. you have to look, of course, at the timing requirements. Those are fundamental. But it's not only about the timing requirements, because there will be an overlap between an RTOS and a Linux with preemptivity, where both could service the same latency requirements. Assuming that is the case, if both are able to meet the latency requirements, then you need to also look at the availability of a reliable update mechanism. You need to look into the security capabilities of both an RTOS and Linux. You need to look at the hardware support, how much hardware, where can you run real-time Linux versus where can you run an RTOS? What are the supporting networking stacks, etc. And on all these other dimensions, that's where a general purpose operating system like Linux with lots more functionalities, support for different hardware features, networking stack, and communication protocols comes into play. So different classes of operating system. One is extremely specialized at just scheduling tasks, but very limited functionality, doesn't have the same security features as Linux, and it's only good at one specific functionality, versus Linux, which is a general purpose OS. It has a lot of functionalities, there's a lot of security features, it often comes with an update mechanism, and with preemptivity, it can serve a lot of real-time workloads. Now, this concludes the first part of this webinar. We saw in relatively quickly what is a real-time system, one with well-defined fixed timing constraints. Our real-time system includes the silicon, the firmware, the operating system, the networking, the user space applications. That's what makes a real-time stack. And every layer must be configured and optimized to support real-time workloads. If we focus on the software side of a real-time system, then Linux with preemptivity is a viable real solution to serve a lot of low latency workloads. And preemptivity modifies Linux kernel in order to give it the capability, the real-time mechanism that are necessary in production. Now, Real-time Ubuntu is a version of the Ubuntu operating system with a real-time kernel. And this is what we're now going to talk about. So we're diving deeper into real-time Linux as a solution for real-time workloads by focusing on real-time Ubuntu. And Canonical, the company behind the Ubuntu operating system, recently we announced the general availability of real-time Ubuntu 24.04. So that's the latest version of the real-time operating system. So let's go into some of the announcement highlights. Now, real-time Ubuntu is Ubuntu, the standard Ubuntu, plus the set of preemptivity patches. And by bringing the preemptivity patches, Real-time Ubuntu changes the default scheduler to one that is priority-based. We do that so that we can increase the predictability of processing real-time tasks and higher priority workloads within the kernel, in such a way that real-time Ubuntu is more preemptive than mainline Linux, because we can deliver higher determinism and lower latencies. An important aspect of when choosing a real-time capable operating system, whether it's a Linux-based one or an RTOS, is often the availability of professional support and the maintenance into the field. Once you deploy your devices in the field, you need to be able to update them, you need to be able to support them and maintain them, because you don't want to be sending engineers to manually fix your device that's already deployed. Now, Real-time Ubuntu is a solution for those seeking long-term support for the kernel and beyond. And what we announced in the latest release is that Real-time Ubuntu comes with a 12-year commitment for security maintenance and support. And we have dedicated professional engineering teams at Canonical that carefully maintain the kernel with preemptivity. They review all the relevant security patches for the kernel. And by enabling this long-term service availability for real-time systems, you can really concentrate your efforts on your value add. You can redirect your resources as an ODM or a device manufacturer towards the activities that bring most value to your organization, because you will know that on the software side, the real-time operating system is being maintained, supported, security patches, and updated for you long term. It's not 1 year, it's not 2 years, It's not even 5 years, it is 12 years of maintenance for your real-time operating system. Now, real-time Ubuntu comes with Ubuntu Pro. What does it mean? So to enable real-time Ubuntu, to deploy it on your device, to test it, to run real-time Ubuntu, you need Ubuntu Pro, which is a free subscription for personal use, and it provides open source software security. It's very easy to get started. In one command, you can have Ubuntu Pro on your machine right now after the webinar. You can find the instructions online. But essentially, Ubuntu Pro brings security, brings compliance on top of the Ubuntu operating system. So security and compliance beyond Ubuntu. It's CVEs for all the software packages that are shipped with the Ubuntu operating system. Ubuntu Pro is vulnerability management for critical, for high, and for selected medium CVEs. And it is open source security coverage for over 25,000 packages that come with the real-time Ubuntu operating system. Why are we doing this? Why are we coupling real-time Ubuntu with Ubuntu Pro, with this compliance and security beyond the OS? Because if you think about what is a real-time system, what goes into making a real-time stack, you have the hardware, and we're going to see in a second where can you run real-time Ubuntu. You have the software, in this case, the operating system, but then you also have applications and packages on top of the operating system. This is why a real-time system includes user space components, networking, etc. And just like every layer of a real-time stack has to support real-time workloads, in just the same way, if you are a device manufacturer running your device in production, every layer of your stack has to be security maintained, has to be compliant, has to be updated, has to be supported long term. So it's not just about the timing requirements of the software, it's about the timing requirements at the hardware level. It's about the timing requirement at the software level. It's about tuning and changing the configuration of your user space applications to take advantage of the real-time capabilities in the kernel, but it's also security and updates and compliance for your entire software stack. This is why we want to couple real-time Ubuntu with Ubuntu Pro. They come together. To get the real-time Ubuntu, to deploy it, to access it, you need Ubuntu Pro, which is very easy. You can look up online how to get real-time Ubuntu. It's a matter of 2 commands on your machines. And by default, if you get real-time Ubuntu, you get everything else that comes with Ubuntu Pro. You get the security and software maintenance for the entire, for your entire open source estate, essentially. Now, I mentioned hardware. We're going to see throughout the rest of this presentation about different hardware where you can run real-time Ubuntu. And one addition compared to the previous version of real-time Ubuntu is that this time we also include optimized support for Raspberry Pi hardware. So we have a specific variant. We have the generic version of real-time Ubuntu that you can run on your ARM and x86 devices, data center, etc. machines. But we also have a specific variant that has been developed, that has been tuned, it has been tested from the ground up on Raspberry Pi in order to give unmatched performance, in order to give optimized latency results on the Raspberry Pi. Everybody has Raspberry Pi at home, and that's why we wanted to give you real time optimized out of the box on the Raspberry Pi so that you can see for yourself the difference in performance, in latency results, in jitter by running a real-time enabled version of Ubuntu and one that is not real-time capable. On the Pi, on a device that you have at home, you can see the results for yourself. And if you're happy with the results, you can then deploy to production with the Pi, if that's your strategy, or depending on which devices you run in production, you can then run Delta Ubuntu on those devices as well. Once you're happy with the performance that you can get this afternoon or this morning on your Raspberry Pi at home, you can then run the same real-time operating system, but a variant that is enabled for your production device. Now, what are some example scenarios of where to run real-time Ubuntu? So I mentioned you can try real-time Ubuntu right now because you probably have a Raspberry Pi at home. You can test it, but Real-time Ubuntu is not only for testing at home, it's for running in production. So this real-time Ubuntu is an industrial-grade solution for enterprises deploying to production. So what we want to do now is to talk about some example scenarios, some use cases and verticals where real-time Ubuntu is currently running, and we have customers and partners currently deploying real-time Ubuntu in those verticals. We will start with Telco. We'll go into some details into the use case for Telco. Then we will focus on the industrial domain. We are also going to see some specific industrial flavors and features that we enable in real-time Ubuntu to be a good solution in industrial. And finally, we'll wrap up by mentioning also other verticals where you can run real-time Ubuntu. So in the telco domain, what are some example scenarios of real-time operating systems? Now, in the telco space, we have the virtualized network functions, VNFs, which are mission-critical services in the telco infrastructure. Also, we have seen the network functions virtualization, which is taking a root in the production environments of telco operators. And in those scenarios, real-time capabilities ensure that those network functions can operate with minimal latency and with minimal jitter. So real-time capabilities, the idea of being able to meet an upper boundary of time, are important for different RAN vendors, for the radio access network vendors, because real-time can enable handling resources very efficiently. You can process data and tasks and handle high-frequency radio signals within an upper boundary of time. And real-time capabilities are also important for improved quality of service. They can give you a reliable and a predictable handling of network traffic. Now, let's focus on one specific production use case of real-time Ubuntu. And to do this, we will consider a scalable deployment of a virtual distributed unit, a VDU, which is one component of an Open RAN architecture. We're going to see how it is facilitated by real-time. Think about a stadium. Now, a stadium is a typical example that could leverage a scalable VDU deployment in a telco domain. If you have a ceremony or if you have an event or a competition that is not yet occurring in your stadium, often the 5G infrastructure that as a telco operator you are running, it primarily is servicing some general communication capabilities. You have your usual requirements with somewhat limited bandwidth, and you have the usual offloading and uploading and transferring of videos and photographs with the medium bandwidth request. This situation is very different when the event actually starts, because in that scenario, you will have a lot of added workload requirements. You're going to have high quality live streaming. You're going to have a huge demand on your bandwidth on top of the generic and usual demand and the generic download and upload as the usual demand goes on. So when the event is happening, you're going to have a massive connection, huge requirement on your bandwidth, and this uploading pressure often leads to very limited wireless connection and to a bad quality of the live streaming. So this scenario stadium, depending on what is going on, whether or not the event is actually occurring or not yet, you're going to have a different balance in the demand of the 5G resources. So what can you do in that scenario? What Canonical with Real-time Ubuntu demonstrated together with Intel's technologies is a scalable 5G VDU technology. So Canonical and Intel solution powered by the Real-time Ubuntu operating system on Intel hardware gives a simple way to have a reliable, scalable solution for this type of 5G wireless technology. So what we demonstrated together with Intel is the auto-scaling of 5G RAN components at the latest MWC in Barcelona. So the setup that Canonical and Intel work together includes a Kubernetes cluster supported by Canonical with the real-time Ubuntu operating system, It includes Intel Flextran reference software and Intel accelerators. And what we show at MWC and what Real-time Ubuntu in Telco supports is a real-life production-grade scenario of a stadium with high bandwidth demands for auto-scaling resources. So to summarize, under normal circumstances, your 5G will serve requests which may include file transfer, messages, general communication, and in general, the utilization of the bandwidth is reasonable and you have some guaranteed SLAs. On the other hand, in case of a massive event, like a competition or concert, your 5G will need to serve requests for applications that may include virtual reality, live streaming, online sharing, and in general, high quality streaming that will require a much more powerful connection, higher bandwidth. And real-time Ubuntu by Canonical is able to support this type of scenario. So this is something that Canonical and Intel demonstrated together. I mentioned Flextran. So in this solution, real-time Ubuntu was running on Flextran. So let's talk about it. In the context of 5G Open Radio Access Network, the use of a real-time kernel would facilitate the communication between different network components. So a real-time operating system support for Open RAN would empower, if you are a telco operator, would allow you to build the high-performance 5G network with lower latency than you otherwise would be able to. Intel's Flextran is an Open RAN implementation that is part of the access network transformation, and you can use it to deploy 4G and 5G cloud-native vRANs. And Real-time Ubuntu supports Intel Flextran. In this way, you can, as a communication service provider, you can see very tangible efficiency gains in your telco workloads. So different companies that are serving the Open RAN ecosystem, you can receive the latest kernel version of Real-time Ubuntu that supports the relevant packages tuned for telco scenarios. So running Flextran on Real-time Ubuntu will allow all the various mobile operators to use the familiar Kubernetes from upstream by Canonical, automation frameworks, and open source tools. So real-time Ubuntu in the telco scenario is a really well-tuned solution in order to support the 5G requirements, the auto-scaling infrastructure, and Canonical, together with Intel, demonstrated the real-life, real-world production-ready solution in the telco domain. Now, that will do for now for telco use cases. How about other verticals where you can run a real-time operating system and in particular real-time Linux and real-time Ubuntu? Let's discuss industrial. In the past, primarily, industrial PCs didn't necessarily support real-time compute capabilities, and they were used mostly for, say, HMIs and data gathering. But we are starting to see in the conversations with partners and the broader ecosystem an increased demand for industrial PCs with real-time capabilities that are driving some of those control systems. Of course, PLCs are part of the story. We are seeing industrial servers that are acquiring real-time capabilities in order to do more of the factory level control pieces. And the same transition is happening in the process industries, from refineries to drilling. If you think also about PLCs in an assembly line, to maintain the system integrity, to maintain the continued production, they must be able to deliver and process data in real time, because a missed deadline could compromise the operation of the entire production line. Of course, the use cases are much broader than industrial PCs or PLCs. You can think about process automation, refineries, petroleum, oil rigs, but also discrete automation, where in manufacturing, where the determinism and the real-time capabilities at the factory floor are needed. Now, in industrial, just like in our ADR scenario, achieving low latency requires careful work at every layer of the stack. just like we talked about in the telco space, it's not only about the operating system, but it's about the reference software like Flextran by Intel, for instance. In the industrial domain, it's not just about the operating system, but it's also the networking part of your stack and the underlying hardware where you're going to run your real-time operating system. So what I'm going to mention now are some optimizations and support done in real-time Ubuntu in order to support networking stacks that are relevant in industrial and which SoCs and hardware real-time Ubuntu supports out of the box in order to facilitate the industrial transition of device manufacturers. Let's start with networking. Now, time-sensitive networking, TSN, it primarily focuses on the network space, and it ensures the time-sensitive applications and workloads receive the necessary processing and network priorities. It's not just about the hardware. It's not just about interrupting the current thread of execution. It's also about receiving the right priority at the network level. And if you want to enable deterministic and low latency communication over Ethernet, TSN ensures that real-time data exchange between the various components. So in this way, you can have the sensor readings and control signals that can be prioritized and delivered with minimal delay, which allows the coordination and the smooth functioning of the different production processes in a factory environment. Now, TSN comes with the time awareness and traffic shaping and allows you to segregate the various data streams from depending on the priority levels. Now, different SoC vendors deliver TSN capabilities for their SoC. TSN is a standard, and then you can have the implementation at the SoC level. For instance, Intel is one of the early vendors delivering TSN capabilities on their Ethernet solutions. And Real-time Ubuntu supports these capabilities brought about by Intel. So you can have the operating system and the networking and the SoC components, all three of those optimized to support real-time workloads. Now, besides network space, the silicon itself, the hardware has to be tuned in order to support real-time workloads. Intel TCC, time coordinated computing, includes a lot of optimizations at the silicon level. It includes cache and memory optimization to be able to allocate the adequate resources. You can manage different interrupt priorities, and you can also synchronize the various clocks throughout the SoC. You can also have temporal isolation. In this way, you can protect the different real-time applications from the impact of other processes that may be operating within the system. And Real-time Ubuntu, once again, supports Intel TCC optimizations at the silicon level. It supports TSN networking capabilities over Ethernet at the SoC level in such a way that you can have an out-of-the-box solution that focuses on every layer of the stack in order to achieve real time in an industrial environment. Now, we also worked Canonical as the provider of real-time Ubuntu together with Intel. We work on emulating an industrial system with real-time Ubuntu on an Intel SoC. So we collaborated together to demonstrate a scalable scenario that showcases a servo controlled by an industrial-grade PC running real-time capabilities. So we have a controller that is running Intel Core, which emulates a workload scenario with both best effort workloads, but also real-time workloads, because you can have the mixed criticality capability within an industrial system. And the real-time workloads is essentially calculating different motor parameters in very well-defined and very precise cycle times. And then those are published via the OPC UA communication protocol over TSN. And what we can then show and what we demonstrated together with Intel is that the motors is able to process its workloads between a very well-defined fixed upper boundary of time. So without the real-time optimizations within the system, both at the hardware as well as the software, the silicon, and the networking space, those best effort workloads would interfere with the real-time workloads. And you would have a missed deadline, you would have a non-deterministic stepping of the motor. What Intel and Canonical demonstrated is that by bringing real-time capabilities, you can have temporal isolation between the best effort and between the real-time workloads. And this really brings the higher determinism and a controlled deterministic stepping of the motor. Now, mixed criticality systems are very relevant they're very common in industrial settings because different applications can have varying levels of criticality, and some may be flexible, some may be safety critical. And what we wanted to demonstrate, real-time Ubuntu on Intel SoCs with optimizations at the networking level is able to service this type of workloads and scenarios. So we discussed real-time Ubuntu capabilities and optimizations in Telco by support for Intel Flexron. We also talked about real-time Ubuntu in industrial with support and optimizations for Intel TSN, time-sensitive networking, as well as Intel TCC, time-coordinated computing, in order to provide temporal isolation at the SoC level and in the networking space. But real-time Ubuntu is not limited to running on Raspberry Pi, to supporting Flexron in Telco, to supporting Intel SoC in industrial and networking applications. Real-time Ubuntu has different variants and different capabilities depending on which verticals you are in. We see truly a wide variety of usage across different markets. And here we have just a high-level view of where those real-time capabilities may be required. So there are lots of broader applications that don't want listed here, but essentially, whether it's in medical or in finance, if you have an upper boundary of time, if you require deterministic processing, then real-time capabilities may be relevant for you. It's also important to understand that because you can have this broad variety of performance and latency requirements, different enterprises will require varying levels of tuning because the cycle times may be different depending on the use case and the markets that you're in. So we see low control cycles in PLCs, and we can see tighter requirements stretching to the microseconds for other applications. So you really have to look, just like you're choosing between an RTOS and real-time Linux, by looking at different timing requirements and the availability of security and updates and support. When you're running real-time Ubuntu or real-time Linux in finance or in automotive or in industrial or in telco, you must look at the precise requirements of your system in order to assess whether or not the tuning, the configuration, and the performance is appropriate for your use case. This brings us to the end of this webinar. So we talked about real-time as a stack, as a system, which comprises the underlying operating system, the silicon, networking, user space applications, and tuning and configuration at every layer of the stack is extremely important in order to achieve the low latency requirements of your precise applications. And we saw how Real-time Ubuntu, which is a Linux distribution with the preempt architecture patches, supports real-time workloads at the software operating system level. But Canonical, as the publisher of Real-time Ubuntu, by partnering with Intel and different silicon vendors and all the players within the ecosystem and the networking space and user space applications and underlying hardware, is capable of delivering an out-of-the-box, fully supported solution that goes beyond just the operating system of real-time Ubuntu. Now, I see you have been asking lots of questions throughout the presentation. Thank you so much for being so engaged, and I will now answer a few of those. Please do reach out for more suggestions, more feedback, and more questions, and the link that is written on the slide. What I will try to do is to group different questions together if they touch on the same topic or the same theme in order to be a bit faster in this part of the webinar. All right. I see there are a couple of questions regarding the version of the Real-time Ubuntu latest release 24.4, as well as whether or not the fact that the kernel 6.8 is end of life affects Canonical's 12-year commitment. So let me clarify here. Real-time Ubuntu 24.4, the latest version of the Real-time Ubuntu operating system, comes with the 6.8 version of the Linux kernel. As was rightfully pointed out by one of the audience participants, kernel 6.8 is indicated as end of life upstream. The question is, does this affect the support commitment by Canonical? And the answer is not. Canonical, what we do, we maintain and we backport all the kernels. We will keep on patching, updating, and security maintaining the kernel for the next 12 years. It's actually an excellent question because this further highlights the importance of the security maintenance. The community version, the upstream version, is end of life, but what Canonical will do is to keep on maintaining and updating and patching the kernel for the next 12 years. And it's really important to run in production software and hardware that is supported, that is maintained, and that is under SLAs. So what we do as a Linux vendors is to support and backport the kernel, and we will maintain Real-time Ubuntu 24.4 with the Linux kernel 6.8 for the next 12 years. Right, let's move on to the next question. Does Canonical recommend any tools to determine the latency on any given system? Well, at Canonical, we use and we do recommend to test the kernel, both cyclic test and stress-ng. Cyclic tests, and if you search it on your browser, you should be probably the first result you find. It's part of the real-time test suite, and it's helpful to measure the latency in your threads, and it's in general a popular tool for testing real-time performance. So you can run it on your system to see for yourself the different results. It creates a series of processes and sees how long they will wait before being serviced. And of course, if you have lower wait times, so much the better. Do pay attention about the unit of measure of those latencies, whether they are, because they are measured in microseconds, not in nanoseconds. And if you are careful, the test run will result in every value being the same because they are rounded to the nearest microseconds. So this was a conversation we had with some colleagues sometimes ago. So do pay attention to the units of measure and rounding when running cyclic tests. We also use stress-ng, and stress-ng allows you to run cyclic tests along with other stressors, which gives you more flexibility when it comes to writing test scenarios. So we do recommend those too. The next question is regarding avionics applications, and I didn't mention those during the webinar. Can you run real-time Ubuntu in avionics? In general, I would say that whether or not you can run a real-time Ubuntu or an RTOS or real-time Linux, it really depends on the latency requirements of your use case and on the consequences for missing a deadline. If the latency requirements are extremely tight and consequence can be catastrophic failure, like it could be in some avionics applications, then an RTOS, a hard real-time operating system, it is capable of performing one single operation, scheduling tasks, may be preferred over a more versatile, with lower overhead, supported lots of functionalities, real-time capable Linux operating system. It depends on the consequences of missing a deadline and on your latency requirements. If your latency requirements are not as tight as the one in, say, avionics, but are still quite stringent, and you have different functionalities that you need to support, then real-time Linux may be a good solution for you. So I don't want to give a yes or no answer. You can test the latency requirements with real-time Ubuntu. You can see the result, and then you should be able to evaluate for yourself whether or not it's a good fit, depending by bringing the factors I mentioned earlier of update, security, and maintenance also into consideration. All right, let's go into the next question. Do we provide examples of communication between real-time and non-real-time processes? In general, I'll mention a couple of things. On the one hand, you can have the use of shared memory is one way to communicate between processes. Other approaches that are worth considering are signals, pipes, sockets, and semaphores. This is part number one of my answer. Part number two is that as an operating system provider, we in general don't bring recommendations for user space application design or example of communication between real-time and non-real-time processes. This is by choice because we provide the underlying platform to our partners who are then in charge of and they have access to the broader hardware software system. And we don't want to provide considerations out of context because without having direct control or access to the environment of a certain prospect. So the choice is a consideration to be evaluated when designing the application and the overall system, how to provide communication between different processes. Now, of course, if there is interest from your side and you're in communication with Canonical, we have a field engineering team that can work with your teams in order to find the best way to architect the broader system. But out of the box, we do not provide user space recommendations because we have no context, no access to your environment. All right, I think we've been running for 50 minutes, and I see some people in the chat have been leaving and have been saying that they need to run to their next meeting. So apologies for running a bit longer than maybe originally promised. I think it was scheduled for 45 minutes. I think we'll end it here, but please do reach out at the link that is provided, the URL that is provided on the slide, and do ask more questions, leave feedback on this webinar so that we can improve, we can do better. There should be also rating functionality. And definitely thank you again for the time throughout this discussion. I hope it has been informative, and I hope you have a better appreciation for the different considerations that may go into making a decision between an RTOS and Linux, between where to run real time, which hardware to pick, and what are some of the factors that have to go into this decision making process. With that said, thank you for your time, and we'll see you at the next webinar.